Shorter Year 12. This is an iterative methods question that's a little bit harder than usual that I'm doing as a request for Sahisnu. So in the examiner report for this paper, it was noted that a number of students had trouble with the first part. And if you take it slowly, I think you'll be fine. But there are a couple of things you've got to watch out for. So we've got a diagram here that shows us two curves. We've got the curve for y equals 4 cosine half of x, which is obviously this one here, right? Obvious because it's starting up here. And then we've got the curve of y equals 1 over 4 minus x. And that's here, and you can see that that's going to have an asymptote out at 4. Right, so what we're looking for is not the point where those two curves meet. Right, so that's what makes this question a little bit different. We're looking for the point A, and when x is equal to A, the tangents to the curves are perpendicular. So we can just grab the ruler to see what we're talking about here. Here's the tangent at point A for that one. And then here's, you can see it working beautifully actually there. Okay, so there's the tangent at point A there, and those tangents are perpendicular to each other. So we have to show that A fits this condition. And then we have to show by calculation that A lies between 2 and 3. And Sahisnu's question here was, how come we don't just show that we've got a change of sign? And what we've got here is we've got two sides of an equation, right? So A is going to be where those two sides are made equal. So what we're looking for here is that on one side we have the left-hand side bigger than the right-hand side, and on the other side we have it the other way around. So we're going to sub in 2 to both sides of the equation here, and then we're going to do the same thing with 3, and we're going to see that we get this switch. So that's one way to do that question. And then we have to do our usual using the iterative formula based on the equation up there, blah, blah, blah. So this is the boring part for 3 marks that you've got to be careful with. So the trickiest bit in this video is the first 4 marks. What do we have to do? Well, we need to show something about the tangents to the curve, so we're going to start off by differentiating, and we're going to get the gradient for this curve, and we're going to get the gradient for this curve. But what do we know if two gradients are perpendicular? Well, we know that perpendicular gradients multiply to give us -1. So this is what we're going to do here, right? We'll find the two gradients, and then we will times them together to get -1, and hopefully that's going to lead us to this condition. Okay, so y is equal to 4 times cos of a half x. So you might want to just pause the video here and do this for yourself, but please watch the solution because there are a few little places to go wrong. So dy by dx for the trig equation is going to be 4 times negative sine half x times 1/2, which gives us -2 sine of a half x. And I'm going to call that m1, right? The gradient for this one, we can see we've got 4 minus x to the -1. So dy by dx will be -4 minus x to the power of -2 times -1, which gives me 1 over 4 minus x squared. Right, so when x is equal to a, the tangents to those curves are perpendicular. So at x equals a, m1, m2 is equal to -1. So we have this condition, -2 sine of a half a times 1 over 4 minus a squared is equal to -1. And just keep an eye on where we're trying to get to. We want to show that a is equal to all of this. And you can see this bit here is fine, so we're going to just start working with this. We get sine of a half a is equal to, so let's get rid of the negative signs, and multiply both sides through by 4 minus a squared, and divide both sides by 2. That gives me 2 times sine of a half a is equal to 4 minus a squared. And you can see where we're trying to get to. We've got a here and we've got 4 here. So this looks like it's come out of an a minus 4. We can see that 4 minus a squared is the same as a minus 4 squared. Now we're going to square root both sides. So we'll get, for starters, plus or minus 2 times sine of a half a is equal to a minus 4. And that gets us almost there. We get a is equal to 4 plus or minus the square root of 2 sine of a half a. But we need to end up with the 4 minus, so we need to justify that. Well, if you think about what we had on the graph, we had x had to be between 0 and 4 because we hit that asymptote out here at 4. So that tells me that a has to be equal to 4 minus root 2 sine of a half a, since 0 is less than x is less than 4. Okay, so we've got the result we needed as required. Okay, that's the first 4 marks. And now we have to verify by calculation that a lies between 2 and 3. So I'm going to do this question in 2 different ways. The first way is one where I just compare the 2 sides. And I'm looking for a switchover of the inequality. So one will start like this and one will be like this. Okay, so when x equals 2, we've got 4 minus root 2 times sine of 1 works out to be 2.7027. And 2 is less than that. So 2 is less than 2.7027. And now I do the same thing for 3. So when x is 3, we get 4 minus the square root of 2 sine half of 3, so 3 over 2 is equal to 2.587. So we've got 3 is greater than that. So since we switch from that to that, and the functions are continuous, the functions on each side, then somewhere in the middle we must have an equality. So there must be a root in between 2 and 3. So that's one way to do this question. Now, the other way is to rewrite this as a function of a. So we can rewrite this as capital F of a, and it's going to be the difference between the 2 sides. So we'll write it as, which way am I going to go? I'll go 4 minus root 2, something bad happening there, 4 minus root 2 sine a half a minus a. Okay, so if I do it this way, then I am looking for a change from positive to negative, right? So it's up to you which method you use. You can either compare the 2 sides and look for a switch from a greater than to a less than, or you can start by setting up a function for the difference in the 2 sides. And if you do it this way and you put in 2, then you get, well, something very close to what we had above. So you get this, and that's 0.703, which is positive. And then when we put in 3, we're going to get this. I think these numbers are all good. I did them a couple of hours ago, and I can't remember what I did, but there we go. So we've got the difference in the 2 sides here is equal to negative 0.412, and that's less than 0. So we've got a change of sign, between 2 and 3, that means that alpha is between 2 and 3. Hopefully your handwriting is not as terrible as that in the exam. Okay, now the very last bit, right, the easy 3 marks but the boring 3 marks. Use an iterative formula based on the equation in part 1 to determine A correct to 3dp. Right, let's just wipe out some of this mess and we'll just work in this space. So let's start with A0 is 2, doesn't really matter. So A0 is 2, so what's A1? So you need to show this, and you want to show it to 5 decimal places, so 2.70272, and then A2 is going to equal 4 minus root 2 sine of 2 times that. Very boring. But actually this is what your calculator is doing in the background, right? So 2.60285, and we can keep on going, so we get A3, 2.61152. So remember, we want to round to 3dp in the end. So let's look at how close we're getting. We're getting 2.603, 2.612, and then I just have to do a couple more steps, and you see it converging pretty quickly here. So the last one, I don't think anyone's watching. I'm thinking maybe Zico is still watching, because last time he said he was. Right, so there we are, A4, and we've got to 2.611, and then A5 is 2.61078. 078, sorry, 2.611 again. So that's our answer. So to 3 decimal places, A is equal to 2.611 to 3dp. So there you go. I think that's a great question to send me into Hisne, so thanks for emailing me with that one. It's just a little bit harder than the usual iterative method stuff. Please keep on sending in any requests, guys, and I'm going to be on Google Classroom tomorrow to answer any other questions.